Hello and welcome to this video on the Hohmann transfer. This video will show you what a Hohmann transfer looks like, the assumptions and the definitions you'll need to know, as well as how to calculate delta V's involved. Let's begin by drawing a diagram to show you the Hohmann transfer and what it looks like. We'll start by drawing the final and initial circular orbits. I'm going to show the direction of the orbits via these arrows. Now to draw the radius of each orbit. RA being the radius of the initial orbit, RB being the radius of the final orbit. I'm now going to label 2 points on the diagram, point A and point B. In an orbital transfer, we aim to get from an initial orbit to a final orbit. In the Hohmann transfer, we do this by a transfer ellipse, which goes from point A to point B. I'm just going to draw the transfer ellipse in using a red dashed line. Might not be the neatest, but at point A, the satellite undergoes a burn, and that's what gets it onto the transfer ellipse from the initial circular orbit. And then at point B, to get off of the transfer ellipse, another burn occurs to then put it onto the final circular orbit. The Hohmann transfer is one of the fuel-efficient transfers. It's coplanar, which means that the initial and the final orbits are in the same plane, or in other words, there is no angle between the initial orbit and the final orbit. It just increases radially. The initial and final orbits are circular. Now, I mentioned previously that this is important, and it is for the maths. The Hohmann transfer goes from the initial to the final orbits via a transfer ellipse. The Hohmann transfer has 2 burns. These are both tangential. The first burn occurs at point A. It's tangential to the initial orbit, and there is a change in velocity, or an increase in velocity, that gets from the initial orbit onto the transfer ellipse orbit. We call this burn, the first burn, delta VA. The second burn occurs at point B. Again, an increase in velocity is needed to get from the transfer ellipse onto the final circular orbit. And we call this burn delta VB. These burns are collinear. Being collinear, we only need to take into account the magnitudes of the velocities. We don't need to take into account the direction. Therefore, to calculate the delta V needed for point A, we need to figure out the difference in velocities from the transfer ellipse and the initial orbit. And from point B, we need to figure out the velocity differences from the transfer ellipse onto the final circular orbit. The last note I'm going to make is that when these burns occur, we are going to assume that they are instantaneous. This isn't complete truth, because in reality the burns aren't going to be completely instantaneous. Previously in the video, we saw to calculate delta V, we need to know the difference in the magnitude of velocities. I've written down the equations for the velocity of a circle and the velocity of an ellipse. G is gravitational constant. Capital M is the mass of whatever's at the centre of the system. In our example, it's the Earth, and it's a satellite going from one orbit to another, but it could just as easily be a heliocentric system where the Sun is at the centre. In that case, if it's heliocentric, the mass would be the mass of the Sun. A is the semi-major axis of the transfer ellipse. R is the radius of the orbits. I'm going to write Gm as mu, but I'm also going to express A in terms of Ra and Rb. If we have a look at the diagram, we see from point A to point B is 2 times the semi-major axis. So if we can figure out the distance between point A and point B and divide it by 2, we will have the semi-major axis on its own. From point A to the centre of the Earth, that's a distance Ra. But from the centre of the Earth to point B, that's a distance Rb. Therefore we can express the semi-major axis as Ra plus Rb all over 2. Delta VA. Previously, we saw that delta VA is given by the difference in the magnitudes of the initial orbit and the transfer ellipse. The transfer ellipse being of the greater velocity means that we'll be taking away from the transfer ellipse. So we'll be taking away the circular velocity from the transfer ellipse. I'm going to write this out in full using the expressions that we have above, but I'm going to substitute in the mu. I'm using Ra on the denominator because it is for point A, and it's the point where the transfer ellipse touches the initial orbit, which has a radius of Ra. I'm then going to input the expression that we derived for the semi-major axis. Simplify by taking the factor of mu over Ra out of the whole equation. Simplify the bracket. And I'm just going to get everything over the same denominator here and simplify from there. I'm just going to move the page down so we've got more space. Simplify the brackets again. Expand out the top and then just cancel it down if there is any cancellations. And this is the final expression that we're left with. Delta VA, as you can see, is given by this expression. We can do the exact same for delta VB. However, delta VB, instead of being the velocity of the ellipse take away the circle, because the final circular velocity is higher than the transfer ellipse, we take away the circle velocity from the ellipse. And instead of being RA, it will be RB. If we do that, then we'll end up with a very similar expression, which is this. These are the expressions that we use to calculate delta VA and delta VB. And that is the Hohmann transfer.